Welcome to today's video. Today we're going to introduce the user level tools to be able to handle tensors in special relativity and formulate it covariantly. Of course, this will be expanded after we learn differential geometry, but for now I think we need to introduce at the very least the basic tools to be able to understand index notation and covariant formulation of special relativity. This video will be necessary in order to proceed to the next video in which we will analyze the Poincare group. So let's get to it. To begin with, we need to introduce a little bit of notation because we're going to start from now on describing relativity with a covariant notation, something that we haven't done so far. By covariant notation, I mean making full use of index notation that we introduced in the first two videos of the course. Now, a little bit of convention before we start. Every time that you see from now on a Roman index starting in I, like I, J, K, L, things like that, those indices are going to run from 1 to 3. They represent spatial indices. Now, when you see Greek indices, a Greek index, mu, nu, rho, sigma, they're going to run from 0 to 3, unless I indicate you otherwise. Now, those are space-time indices. We will associate the 0 value of that index with a time component, as we will see in a second. Now, consider a reference frame S. Remember, a reference frame is associated with ability to measure in all directions of space and ability to look at the time, measure time. So let's see that we have an orthonormal basis of 3 space, E1, E2, E3, and then a clock, which measures the time t. Every point in space-time then is characterized by a position, vector x, a position vector, with components xi, and this is just telling me that is the sum of the elements of the basis with the corresponding component, right? A linear combination of elements of the basis. And remember, this is an Einstein sum, repeating index up and down. And a time t, that characterizes every point. We can build a higher dimensional structure, putting together, so the idea here is we're going to put together, in some sort of vector space, we're going to put together the time and spatial coordinates in a vectorial structure. Now, how are we going to do that? Now, let's consider the component again. We will see more of this in the context of differential geometry, how to assign coordinates to a differential manifold, but we're not there yet. For now, let's think of this following construction. We get the spatial components of x in that basis, E1, E2, E3, and then I gather them together as components of something called 4 vector, together with the time component in the clock associated with a reference frame, so that I write, look at my notation for 4 vectors. Now, spatial vectors have arrows, 4 vectors have serifas. Okay? So as you can tell, we have the serifa here. This is the vector, the abstract object, and these epsilons here have serifas as well. They are vectors. So this is an equation analog to this one. I have the components of the 4 vector being the coefficients of the linear combinations of elements of this set, epsilon 0, 1, 2, and 3. Now, the 0th component, I associated with the time coordinate, I add the c multiplying t, so as to have all the components with the same dimension. If these ones are spatial dimensions, this one also have spatial dimensions. Now, xi are the components of x vector in the basis E1, E2, E3 associated with the frame S. And x0 is c times t, where t is the time as measured by the clock associated with the reference frame S. I have introduced to put them together as a vector, something like a 4-dimensional basis with 1 vector of the basis going in the time direction and 3 other vectors going in the spatial directions. Now, we call this set that we abbreviate with epsilon mu. So you have the epsilon mu here, that means that mu runs from 0 to 3, so this set is the same set as this in abbreviated form, and this is a Lorentzian basis. Now, notation-wise, oftentimes you will see people calling x mu a 4 vector out there. That is an abuse of notation, an abuse of language. That is not a 4 vector. If people tell you the 4, I may tell you even later on the 4 vector x mu, but that's not really a 4 vector. What we actually mean is the components of the 4 vector x. So the 4 vector x is the abstract object, the 4 vector. X mu is its component. So x mu, you can write if you want as a column vector if you want. For example, I don't know, if it's a position 4 vector, ct, x, y, and z. Because of course this is the x0, x1, x2, x3, and typically we call x0 ct, we call x x1, y x2, and z x3. All right. So this is the typical notation. When people tell you this is a 4 vector, well, you know that what I mean is these are the components of a 4 vector. Okay, which of course is one-to-one given a basis. Given a basis is one-to-one with defining the vector. Okay, but the abstract object can be defined without having to refer to a basis. We can express it as a sum of elements of a basis by doing this, of course, the components times elements of the basis. Now these objects, this is an abstract vector, these also are abstract vectors. In fact, I can write these abstract vectors if you want. What are the components of, let's say, epsilon 0 in the basis epsilon mu? Well, that's easy. Epsilon 0 is the vector in the direction of time only. So epsilon 0 is going to be epsilon 0 component mu if you want to collect them to gather them in the same way as I did this in a column vector, that will be 1, 0, 0, 0. Okay? All right. Now, we will see more of this, of course, when we see differential geometry, but at the very least now, we know how to conceive a little bit of an idea of the vector space that you can put together using the time component together with the spatial components, characterizing points from in space-time from the point of view referred to a reference frame S. Okay? Every reference frame S defines a basis of space-time, okay? Of this vector space that we use to characterize points in space-time. All right, if I want to write, just for finishing, epsilon, 3 mu, the components would be 0, 0, 0, 1. All right, you see how this goes. The same way that we will write, for example, for the spatial ones, what are the spatial components E1i of the vector E1? Well, you usually write it in a column vector. If you want to write them as 1, 0, 0, right? So E1 is 1, E11 is 1, E12 is 0, E13 is 0, right? Okay, I hope that this is clear. Now that we understand how to build this vector space that represents, in a way, points in space-times, made out of points in space-time, let's now revisit the line element and try to learn something about the way we can write this. First of all, let's review the space-time interval. You remember the space-time interval, which is defined between two events. It's defined as this expression here, which we can write now in the new expressions that we have in terms of coordinates of this new four-dimensional vector space as minus delta x0. Remember that x0 is ct, so literally the c comes out, and that's literally delta x0 is exactly the same as c delta t. So delta x0 squared plus minus delta x0 squared plus the sum of the squares of the deltas of the spatial components. That allows us to classify relationships between pairs of events regarding to what is the separation between, what is the space-time interval between them, at least what is the signature of the space-time interval between them. We have, imagine that I draw, let's consider a one-dimensional case where there's only x1, 1 plus 1 dimensional, 1 dimension of time, 1 of space. So you have x1, x0, which is the same as saying that this axis is ct and this axis is just x, right? Okay. And then we have the 45. So let's say that I have an event at the origin and another event that I'm going to place at different places. So I can draw a 45-degree line here and here. And I say, okay, now I have two events, this event and this event. Well, you can tell that the separation between them is larger in time than it is in space. This is delta x0 and this is delta x1. Delta x0 is larger than delta x1. So obviously, if delta x0 is larger than delta x1, we're going to have that this is going to be negative. So these two events are time-like separated. It would be this case. Now, if I consider this other event, these two events, the one at the origin and this one, the delta x1 between them is larger than delta x0. These guys are, for this, the delta s is going to be positive. These two events are space-like separated. Of course, if I place these events now, let me just do a quick modification and place them on the 45-degree line, then delta x0 is going to coincide with delta x1, and therefore they're going to be like separated. Of course, I just put one in the origin just to make it easier to see, but this is not, the relationship is not between the origin and another point. The relationship is between 2 points in spacetime. If I place one point here and another one here, then I draw the 45-degree line here, right? Right? It's called the light cone, but we will talk more about that. That's supposed to be 45 degrees. I mean, my drawing skills, you know, only go so far. And this is supposed to go like this, right? So this event, so you call this one E1 and this one E2, these two events are time-like separated because you see that we have to do this amount of spatial separation, this amount of time separation. All right, so that clear? Let's check the line element and let's see if we can write the line element in a way that is screaming covariance. So we have the line element here, and we can write the line element in terms of this expression in coordinates based on a basis associated with a reference frame of the space of 4 vectors. Remember, x0 being ct, x1 being x, x2 being y, x3 being z. And with that, we can write the line element like this. And now we can wonder, all right, this looks a lot like some sort of quadratic form, isn't it? Let's see. I can write ds squared as some, if you want, 4x4 matrix that I call eta mu nu, those are the matrix elements, acting on the vectors made of differentials, like that. Remember, so if this is x mu, dx mu would be dx0, dx1, dx2, dx3, right? So I can write like that, and I can wonder, okay, what are the entries of this matrix? So basically what I'm asking is I have, all right, this ds squared is, I contract the first index, so it's some dx0, dx1, dx2, dx3, and then some matrix, eta mu nu, 4x4, and then I have here dx0, oops, dx1, dx2, dx3. So these are the matrix elements eta mu nu. Oops, sorry, eta mu nu. All right, and I want the s squared to be a product, if you want, of this, as I wrote it here, a row vector, a matrix, and a column vector. So it's contracting two indices. So you see how having index up or down is not related to being column or or row. I can represent them as I want. And this is what it is. So I contract the first index. So remember, to contract the first index, I would need to transpose. That would be the same as in the representation as considering a row, and the other one as a vector considering a column. Anyway, so you can tell if you write here eta 0, 0, eta 0, 1, eta 0, 2, eta 0, 3, and you keep going, eta 1, 0, and so on and so forth. Okay, what you obtain is exactly that this is the same as that. This is a double sum, right? All the possible combinations sum together. This thing would be eta 0, 0, dx0, dx0, plus eta 0, 1, dx0, dx1, plus etc. All right? It's a sum in the two indices. Now, we can ask, what are the values of these entries? We know what this has to be because I know that this is going to be minus dx0 plus dx1 squared plus dx1 squared plus dx2 squared plus dx3 squared. So they don't mix with each other. I know the non-diagonal terms are going to be 0. And the diagonal terms, what are they going to be? Well, I can read them. A minus, a plus, and a plus. So let's write down that. Sorry. Right, so if this matrix, again, that matrix elements and eta mu nu is minus 1, 1, 1, 1, then this thing's exactly equal to minus dx0 squared plus dx1 squared plus dx2 squared plus dx3 squared. So wonderful. I can write the line element ds squared as this matrix eta mu nu acting on two copies of the differentials associated with the coordinates x0, x1, x2, and x3. So we're going to write the matrix eta. Allow me to write a little bit better, like this. And this matrix eta, I'm going to say, is the components in the basis upsilon mu of something that I'm going to call the metric tensor. I mean, I don't even know if it's a tensor, but I'm going to use it like when you name your pets, right? Imagine you have a dog that is very small and you call that dog Superman. Well, it's not that the dog has superpowers, it's just a, you know, a friendly way of calling the dog. But maybe tomorrow the dog freaking shows superpower and it's weakened by kryptonite and has X-ray vision and all that stuff, right? So if that Superman has X-ray vision, I don't actually know. Okay, let me try again. So we're gonna call this matrix the coefficients of the metric tensor, eta. That is gonna be the matrix elements of the metric tensor eta acting on the basis upsilon sub mu. I'm gonna tell you in a second. Now, I call it a metric tensor, but I don't even know if it's a tensor yet. It's like when you have a pet and you give it a nickname to be just calling them fondly. For example, you have a little dog and you call the little dog Superman. But then maybe the day after you discover that that dog is dating somebody called Lois Lane and has you know, aversion to kryptonite and can fly and has heat vision and things like that. Well, if it happens that in the end is Superman, you are lucky and you will call your dog the way you should have called it from the beginning. But you don't know yet. When you gave the name, it was just fondly. That's what we're doing here. We don't know if eta is a tensor. We're gonna call it tensor for now, but we will see if the name is justified. Now again, have this tensor eta of components eta mu nu, and of course eta mu nu is this tensor acting on the elements, on two copies of the elements of the basis. This is what we call eta mu nu. All right, so these are the matrix elements of eta in the basis upsilon mu, having two copies of the basis and acting twice. And if you want to represent it as a matrix, it's like getting, okay, if I want the 1, 1 component, I act with the vector 1 on one side, I put minus 1, 1, 1, 1 here, and I act with the vector 1, 0, 0, 0 on that side. This thing is upsilon 1, upsilon 0. This is upsilon 0. And acting, I get that this component is just minus 1, which is of course the eta 0, 0 component. If you want another, just modify. If you want the 1, 0, so this thing is 0, 1, this is upsilon 1, and of course you get that this is 0, and this is 1, 0, and of course 1, 0 is right here, Okay, so you get nothing, you get 0. Now if you want the 2 component, well, you write upsilon 2 here, upsilon 2 here, you compute, and this gives you eta 2, 2, and that is a 1 in here, right, which is this one here. 0, 0, 0, 1, 1, 2, 2, 3, 3. I hope that this makes sense. If not, please make sure that you bring your questions to the review session. But yeah, you can tell that if I define the matrix elements of eta mu nu like minus 1, 1, 1, 1 in the diagonal, then this thing is exactly equal to the line element. All right, to check if this is actually a tensor, a twice covariant tensor, that's what it should be, well, we need to check if this thing transforms like a tensor on the change of basis. So the test that we need to do, remembering and recalling what we saw in the second video we recorded, if eta is a 0 to tensor, a twice covariant tensor, as it should be, if it's got two indices downstairs, and that's what it should be because the x's, the differentials here have an index upstairs, okay? So I need that this thing transforms, then eta mu nu prime has to be equal to lambda mu sigma lambda nu rho eta sigma rho. That's what it has to be true if eta were a tensor. Now, question, does eta transform like that? Well, let's see it. Now, let's imagine that the lambdas here, when I represent them, is a change of basis, mapping it from one reference frame to another reference frame, okay, between two inertial reference frames. And then we know that the line element is invariant at the changes of reference frame. That's kind of cool. So if I write the line element ds squared, and I write it in a different basis, in a basis of coordinates associated with a different reference frame, say that I have another one, let me call it x prime, right, mu, and this is going to be equal to x prime 0, x prime 1, x prime 2, and x prime 3. Then, of course, the dx prime mu is going to be dx prime 0, dx prime 1, etc., right? And now, because I know that x prime and x are vectors, they transform on the changes of basis with lambda tilde. Remember, so x prime mu would be equal to lambda tilde mu nu x nu, where lambda tilde, as a matrix, if you remember, is lambda inverse transpose. Okay? This is true for the vector, for the position vectors with the coordinates. This is also true for the vectors containing the differentials, right? So I write a D here, and this is still true. All right. Now, let me do a Lorentz transformation then implemented by lambda tilde on the vectors. I'm moving from a coordinate system S to an S prime, okay? From these coordinates to these coordinates through a lambda tilde. And I know though that ds squared doesn't change because it's a Lorentz invariant thing. If you do a Lorentz transformation here, it will remain the same. So we know that in a different reference frame, I would have the line element, of course, ds squared equals minus c squared dt prime squared plus dx prime squared, which is the same as minus dx prime 0 squared plus dx prime 1 squared plus dx prime 2 squared plus dx prime 3 squared, right? So I wrote here that in the new coordinate, the prime coordinates, of course, the line element is going to be equal. You're going to have the same form, only with the primes in here. And you see, the matrix eta mu nu in this set of coordinates with eta prime mu nu would be exactly the same entries, right? So it is also true that I would have eta, let's say, sigma rho, and I have dx prime sigma dx prime rho. It will still be true. Now, of course, these are the transform ones to the, I need to get those vectors and transform them to the new basis, but it has to be true that the elements are still minus 1, 1, 1, 1. Now, let me write the transformation explicitly. So let me write here a little wormhole. All right. And I know, well, I'm going to write again ds squared. Has to be, I'll write the left-hand side again, mu nu dx mu dx nu. And I'll write here, I'm going to write explicitly the transformation. So that would be eta sigma rho. And then the first one, it's going to be a transformation that is going to be sigma mu dx mu, and then with a tilde, of course, and then lambda tilde, and I have rho, and I have nu dx nu. All right, and then you can tell that this little thing is the transform. The transform, applying the lambda tilde to dx nu gives me dx prime, right? Mu. And that's what I have here. Applying the lambda tilde to dx nu, I get dx prime rho. And same thing for this guy. Eh? This is this. The same thing. But now we can reorder this and write this as eta sigma rho lambda sigma mu with a tilde, and then lambda rho nu with a tilde, and now dx mu dx nu. Aha! So I have on the left hand side I have this, on the right hand side I have this, and these two things have to be the same. All right? Well, if these two things have to be the same, I can equate the coefficients because the components of the vectors with the differentials are the same, and I get that eta mu nu has to be equal to eta sigma rho
lambda tilde
sigma mu
lambda tilde
rho nu. All right, so we obtain that equation. Now, let's start from this equation that we just obtained, and let's manipulate a little bit to see if we can prove this kind of identity. Let's do it. So, what do we know so far? We know that, as you can tell from here, in different inertial reference frames, in coordinates associated with different inertial reference frames that are related by transformations that are translations, rotations, Lorentz boosts, and time shifts, the coefficients of eta mu nu, the coefficients of that metric tensor, is the same, minus 1, 1, 1, 1, minus 1, 1, 1, 1. So we know that eta prime mu nu equals eta mu nu. Wonderful. We also proved right now that eta mu nu is equal to eta sigma rho, and then the lambda tildes, remember the inverse transpose of the change of basis matrix, contracted with two lambda tildes like that. Now, to be able to call it tensor, what we needed to prove is this. And so far we haven't proven it. This is not what we got. We got lambda tildes, not lambdas. So we need to work a little bit more to prove that and to be able to declare this a tensor. Okay? Now, let me introduce well, we know that lambda and lambda tilde are inverse transposed with each other. That means that this identity is true, right? If we have lambda nu mu and lambda tilde rho mu, this is the identity delta nu rho. Okay, this is rho. Now, do you see this relation? If you don't see it, try to derive it, pause the video, and then continue and let's see it. We know, remember, that lambda nu mu and then lambda inverse, okay, let's call it mu rho, that thing is the identity rho nu, right? But then lambda tilde is the transpose of this guy. So if I write lambda nu mu and I transpose twice, so I do lambda minus 1 transpose, but I also swap the two indices, so I do the transpose twice, rho mu, this is still the same thing because I've done nothing, right? And because of that, this thing is directly lambda tilde by definition, lambda tilde rho mu, which is what I wrote here. So that's the proof of that little identity. Okay? All right, so we have these three things that we know of. Let's apply them and let's try to prove that this thing is actually a tensor and therefore it's okay to call it the metric tensor. We need to work that much to call it the metric tensor, not because somebody with a mustache arrives here and tells you that's the metric tensor. You have to believe that this is the metric tensor. So no, we're gonna have to prove it. And this is good practice for later. So let's prove it. I'm gonna get this equation and I'm gonna multiply both sides by the same quantity. So I'm gonna have eta mu nu lambda kappa mu lambda beta nu. This is multiplying the left hand side by this quantity. That also means that I'm going to multiply the right hand side by the same amount. Eta sigma rho lambda tilde sigma mu lambda tilde rho nu, and then I have lambda kappa mu lambda beta nu. All right. Now, all that we do now is reorder this a tiny little bit so as to have the right products, and then we get that this thing, I'm gonna do it as a step. It's eta mu nu lambda kappa mu lambda beta nu equals eta sigma rho, and then I pair them. I'm gonna pair these two. I'm gonna write this one first, so it's lambda kappa mu and then lambda tilde sigma mu, and then I'm gonna pair this with this one, so lambda beta nu lambda tilde rho nu. All right, so all that I did is rearrange, right? I move this one here and I move this one here. Okay, now the nice thing to realize is that when we have a lambda with the second index contracted with the second index of a lambda tilde, that is exactly a delta, an identity. So we realize that this is exactly an identity, second with second, so we get a delta kappa sigma, and we get a delta here beta rho. Oh, that's nice, because that means that, look at what we have. Let me write this side first. I'm going to write the right hand side as left now. I have eta, what would that be? The sigma becomes a kappa, and the rho becomes a beta. Okay, this is this. It's equal to eta mu nu lambda kappa mu and lambda beta nu. Oh, look at this. This looks more like that. Now, if we wanted to write these two things equal, so the one that we're looking for will look more like this. Eta prime kappa beta, just using the same names of the indices I have here. should be eta mu nu, then lambda kappa mu, lambda beta nu, right? We don't have that, but we actually do, because we know the components of the matrix elements, the two bases are the same. So using that, I know that this is exactly equal to eta prime kappa beta, and this is the transformation that eta has to have in order to transform as a tensor. So yes, we're vindicated. We just proved that eta mu nu, what we call the metric tensor, it's actually a Lorentzian tensor. It's a tensor under transformations of inertial reference frame. Transformation of coordinates associated with inertial reference frames. It's like the day your dog now stands up, takes the glasses off, and wears a red cape and starts flying, and you realize your dog that you call fondly Superman happens to be the real Superman. That's the thing, vindicated. Eta is a twice covariant tensor that happens to also be symmetric. And if you remember your video, that is exactly a metric tensor. So we can use eta mu nu as a metric tensor. Recommendation: given that this is a video, please rewind and go through all the calculations, and if you have questions, do ask in the review sessions, because this is very basic index notation calculations that can be very challenging if you've never done it before. So please do it as practice and ask if you have questions, because the exercises that you will get in assignments will be more difficult than this, okay? So do ask all the questions you have, and if you don't follow something, ask me to walk you through it. And please make use that this is a video. It sucks in many ways, but you can rewind and watch again. All right, now that we have that this is a tensor and we can call it a metric tensor, let's now do the thing that we did with metric tensors in video number 2, shall we? So now we know that because we have a metric for every 4 vector of components v super mu, I can define a covector, something you see, remember this thing is contravariant, has one contravariant index upstairs. I can define an object that has one contravariant index downstairs that is related to v by the metric, like this. So we use the metric to lower the index nu downstairs, and it becomes a sub-index. So I define the components of the covector v through the components of the vector v using the metric to lower the index. Wonderful. Now remember that we can now use, using eta minus 1, because remember that a metric needs to be non-singular, so I didn't tell you that before, and I should have. The metric has to be non-singular, and it is because the eigenvalues were minus 1, 1, 1, 1, so there's no zero eigenvalues. We can define the inverse, and in fact, it so happens that the components eta mu nu, eta super mu nu, which are the components, these things are the components of the inverse metric, happen to be the same, right? If you compute the inverse of the matrix minus 1, 1, 1, 1, you find that it's the same inverse, right? It's easy to check, right? Eta, do you remember that eta mu nu, eta, let's call it nu rho, has to be the identity because it's inverse one of each other, so mu rho. Well, let's do that matrix product. So you have minus 1, 1, 1, 1, multiplied by minus 1, 1, 1, 1. What is this? Well, this is literally 1, 1, 1, 1, so the delta. You see, the matrix elements of the metric are the same matrix elements as the metric inverse. So it's very easy in this case, but you can tell that the components, that with eta mu nu, we can do the opposite. We can define, for every covector, or covariant for vector, let me just write it properly, covariant for vector, let's call it v sub, or omega, let's call it omega sub mu, then we define a vector, a 4 vector, contravariant, let me just write it properly, a contravariant 4 vector that is going to be omega super mu equals eta mu nu omega nu. Okay, so we can lower and raise indices with a metric. We can associate for every vector a covector, and for every covector a vector. All right, wonderful. So this actually allows me, well, let's do two things. The first thing to realize is that the components, so if I give you the following vector, and I ask you to tell me what would be the covariant, the one with the index down, what would be V with the index down, then you know that V with the index down would be equal to eta mu nu V nu. V sub 0 would be equal to eta 0, 0, V super 0. Well, of course, there will also be eta everything else, right? 0, 1, V1, etc. But remember that eta 0, 1 is 0. All the non-diagonal components are 0. So all that we get is that V0 is equal to minus 1 multiplying V0. So the signs change. If I want to write, let me write just for your comfort, this as a row, even though I don't have to, but let me write as a row, that would be minus 3, 7, 9, 1. Okay? Because of course V1 would be eta 1, 1, V1, and this thing is a 1, because remember that eta was minus 1, 1, 1, 1. Okay? And therefore, the second component is exactly the same signature. All right? Okay. But you see now that the bras and the kets, this is the ket, this is the bra, they're not, there's a sign of difference between the components of each other. All right. Finally, we can define a structure of inner product and norm now that we have a metric. Let's do that. So I define this notion of inner product in which I get two vectors of, 4 vectors, you see with the serifa after objects, characterized in a basis by these components, the components V nu and the components W nu. And using the metric tensor, I get that this thing is an inner product. Like for example, like if I were, imagine that I give you V mu equals minus 1, 0, 1, 0, and W mu would be 2, 1, 0, 0. All right? Maybe let's remove the 1 to make it easier. What is the inner product between these two things? Well, let's compute it. The inner product, the Lorentzian inner product between them, it's equal to, I can do it as a matrix product if I want. I can put the V like that, 1, 0. I put the metric here, which is the same as doing the sum, 1, 1, 1. If you remember from the second video the first video that we recorded. And then 2, 0, 1, 0. All right, so if we do that, we see that we get that is 1 times minus 1 times 2 plus 1 times 1 times 1, because all the other entries are 0. So this thing is minus 2 plus 1, which is minus 1. All right? So the inner product between these two vectors is not the sum of the products of the entries. Now what I've done, you can see now that every time you can generalize the definition of inner product like that, and then you get the famous inner product that you were using for Rn by putting the identity here. If this matrix, instead of being minus 1, 1, 1, 1, was 1, 1, 1, 1, this is the way you've been doing the dot product all your life in R4, right? But it's not like that, and in relativity it will not be like that. And in curved spaces, this thing will also have non-diagonal elements as well. So we have to be careful, and that's why we have to be careful this time when we talk about inner products and when we talk about norms of vectors. Because the interesting thing about this metric, as opposed to the metric of Euclidean spaces, which is when you have the identity, you call it a Euclidean space, is that the signature of this metric is not positive definite. So that means that when we compute norms, let's see what we find. The norm of the vector v, which we notate norm of v squared, I mean, I define the norm squared, even though I will call it the norm all the time, so I will define it like that with a square, is the inner product of v with itself, right? And it's, of course, the contraction of the vector twice with the metric. So remember how we did an inner product between v and w, just take w to be v as well. We also can sort it like that, right? Because remember, this thing is lowering the index of v, so this is v nu, as we saw before. And this product can be, but let's see what it is for several examples. Let's compute the norm of these 3, 4 vectors and see what we get. The first one, well, this one, if I compute the norm of v squared here, this is equal to v mu, which is the same as eta mu nu, v mu. This is the same as writing two nus here, exactly the same thing. This is equal to, well, all the components are 0 except for the 1, 1 in this case, so it would be eta 1, 1, v1, v1, and therefore that thing would be, in this case, is 1, 1, and 1. Wonderful. So this is 1 for this one. It's a unit vector of norm square 1. Wonderful. So how about this one? Well, this one is slightly different because what I get, which is the same thing, v nu, same thing as above, even though it's a mu, but it's the same thing, of course. It's training you and not to be bothered by that. Mu nu, v nu. Now, the thing is that in this case, all of them are 0 except for the 0, 0 component, 0, 0, v0, v0, and this thing now is minus 1, 1, and 1. So this thing is minus 1. So that thing has norm square that is negative. Aha! So it is something that in Euclidean spaces is not allowed. The norm square cannot be negative, but in Lorentzian spaces, we relax that and we allow it because otherwise we can't do structure of spacetime. This is, we have extended our metric not to be positive semi-definite. Usually for the metric in Euclidean spaces, we demand that it's a twice covariant tensor that is symmetric and also that is positive semi-definite. We relax that. It's even worse because in terms of bothersome differences with the Euclidean case, what about this vector? Well, this one has norm v nu, v mu, same thing as before, nu, v mu. In this case, we have two entries. We have eta 0, 0, v0, v0, plus eta 2, 2, in this case, v2, v2. So this one is minus 1, 1, 1, this one is 1, 1, 1, so this is 0. So this one has norm 0. And not only that, remember that when you defined your vector spaces that had a norm, when you have a vector space with a norm, usually you demand from the norm that the only vector for which it will be 0 will be the 0 vector. Not in this case. We have an infinite number of vectors that have 0 norm. Well, if I write here a 9 and a 9, this is also 0, and I have an infinite number of combinations as long as the time part cancels all the spatial part. So these vectors, right, I can classify into vectors depending on the three kinds of vectors depending on the signature of their norms, norm square. So like this. If the norm square is positive, we call the vector space-like. If the norm is negative, norm square is negative, we call it time-like. And if the norm is 0, we call it null vectors. So you see, this vector, if this is x and this is ct, right? x1 and x0. This vector would be space-like, this vector would be time-like, and any vector in the diagonals, like this, or like that, or like that, or like that, they would be null vectors. One final thing that I want to tell you about before moving into the Poincaré group, which will be in the next video, is for differentiation. Now, let me define the for gradient operator, which is partial mu. Okay, so that operator is, of course, you can think of it as a vector in a way that contains, let me just write something here to orient you a little bit, contains partial with respect to time, to x0, partial with respect to x1, partial with respect to x2, partial with respect to x3, right? So partial mu is, the definition of this guy, is partial x mu. Now, super important, when you're taking derivative with respect to something that has an index upstairs, the derivative, the gradient, has an index downstairs. We will understand that much better when we see differential geometry, but you can tell already that on the changes of basis, this thing will transform covariantly, not contravariantly. If this thing transforms contravariantly, this thing transforms, if x mu transforms contravariantly, partial mu transforms covariantly. This is a nice exercise for you to do that we will certainly do in full detail when we see differential geometry, but that you can do right now even to train yourselves. If I apply this gradient to a function, this is the same, of course, as partial f, partial x mu, right? And this thing would be a vector made out of, if I represent it like that, it would be a vector which would be the partial with respect to x0 of f, and then the partial with respect to the spatial ones of f, right? Now remember that the partial with respect to x0, partial 0, is partial x0. So if you want, this thing is partial with respect to ct, okay? So this is the same as 1 over c, partial with respect to t, all right? Be careful with that C factor when we write the C's. In general relativity, we will quickly move to natural units, but in special relativity, we're keeping the C's for reasons that we will see later. But just remember this and be careful with the notation. Notation is very intuitive. For example, what would be if I apply partial mu to x nu? What is the result of that? Maybe pause the video and try to guess it. If not, I'm going to solve it right now. So what do you think it is? So if nu is equal to mu, it would be 1. So let's see. I know that partial 1 of x1 would be 1, right? But partial 2 of x2, this is the same as saying partial y of y, but that's also equal to 1. But what about partial 1 of x2? Well, that's like the same as saying partial x of y, which is 0, right? So this thing would be the identity, mu, nu. This will be only 0, will be only non-zero when you're taking the derivative with respect to the same coordinate that you have in here. If you have a different coordinate, it will be 0, because that's a partial derivative with respect to another coordinate. All right? So again, these things, make sure that you control them well and that you understand them well. It's nothing but an abbreviated notation for the derivative, for the gradient, that is now consistent with the tensor structure of the objects that we're seeing. Things to remember. The gradient has a covariant index, okay? Not a contravariant one. And second, well, remember that those are the derivatives with respect to x0, x1, and so on. And there is a C in the definition of x0 with respect to time. All right, we will be talking much more about these things as we go more into more rigorous formulations in terms of differential geometry. But for now, you learn the user level to be able to do special relativity properly. The next thing we're going to do is analyze the Poincare group, and in particular the Lorentz group that includes rotations and boosts that I don't separate for a reason that we will discuss. That will be in the next video. See you then. Until then, take care.